So welcome back. So I wanted to, I started with this last time. I want to continue this today. While this course is really about expansions of the real field, I want to do this one lecture where I somehow put this in this kind of larger generality of expansion of the real additive group, and I will hopefully finish that today. To review, last time what we introduced was this kind of notion of a dense omega order set. So that's just to, for now, as I said, in an expansion of the real additive group. And then a dense omega orderable set was some kind of definable order. Well, if it's just an omega order, then we just mean that it's definable. And that the order type of this definable order is omega. So order type omega means that it's order isomorphic to the naturals with order. Dense, so when I say dense omega order, then this is really just a short form for saying that D, so this underlying set, is a dense, so just somewhere dense, but not with respect to the order we're adding, with respect to the usual order of this. So as a subset of the reals. So D is a subset of the reals and somewhere dense with respect to this usual order. So there are really two orders living on this D. The one is this very discrete order, and the other one is this dense order. Last time I gave an example that if you, so last time, if you have function like this definable, and this one here is, let's say, closed and discrete. D is closed and discrete, and the subset, let's see, of the positive reals. And suppose that f of D is dense or somewhat dense, then f of D was one of these dense omega orders, or can be, there's some order that this is a dense omega order. And the order you get is simply, we said that if you know that a set D is omega orderable, then any power is omega orderable. And we said that if you have a set that is omega orderable, then also the image is omega orderable. Okay, I want to give one more example of omega order, because this will also become more important when I talk about the field. This is really kind of one of the core observations where this kind of omega order comes from to begin with. So this is, my notation keeps being correct, and I think if I'm now with 2.6, and this should be some example. So here what we want to do is we want to, so let C subset of R be a Cantor set. You won't think of a Cantor set as the usual ternary Cantor set. And but in general, this means that C is compact. So this is not a traditional Cantor set. It's a compact set without interior or isolated points. So now what I want to show is how this gives rise to the omega orderable set, one omega order, if you put the C as onto the real additive group. And the first thing for that I want to introduce is really just a name. So we say that an interval, is a complementary interval of Cantor set C. Well, if it is really just an interval, it's just one of the connected components of the complement of C. So C is if I is a connected component of the reals. So the picture you should have in mind, I'm glad that I can also draw a picture for a change. So if you, let's say, take your ternary Cantor set, I mean, how do you get your ternary Cantor set? You get this by removing the middle third intervals, right? So the middle, so this is 2/3, this is 3/3, so this is your first step. And then this one here would be your first. So this would be one of these complementary intervals. And of course, you keep on doing that. So then the next step would get throw this away and this away. This would be, what is it, 1, 9, 2, 9, 7, 9, and 8, 9. And so then the next complementary intervals you get would be these two. And down here, at some point down here, you would have the Cantor set down here with all its kind of complementary intervals. Okay, come back to this drawing in just a second. And so now we want to come from this Cantor set, from this really some sense sparse object. We want to find an omega order. And the way we're doing that is we're going to use the length of the complementary intervals. So I'm now going to define this function. Well, first, okay. I'm going to define properly the set I want to look at. So what I'm going to do is I take L to be the left endpoints of complementary intervals of C. I mean, note, and this is a very easy exercise, note that L is definable in, if you take the real additive group and you add C to it. So that's really easy to check. And now, so now essentially we are associated to each of these intervals, we associated a point, so the left endpoint. So if you color here, this would be a red, it's supposed to be red. So these would be endpoints. And so now for each of these points, of course, we can associate to it the length of that interval. So it's simply, I mean, you take the supreme, I mean, you take the infimum of everything in C that is larger than this point, and you get that point, you take the difference, and you get the length. So we define now for each of these points, so the length of the complementary interval, so that I actually want, I think I should say bounded here. Okay, so then I forget about the point on the, in this case of the picture I draw, I forget about 1 because that's the length of that interval is infinite. And so now I take, let's call this map tau, be a map that maps L to R and maps, maybe X is a good name, maps, takes one of these endpoints and maps it to the length, X to the length of the of the complementary interval whose endpoint, whose left endpoint, interval whose left endpoint is X. Okay. And so, so now if you want to So this gives us, this really takes this set L and gives allows you to order this set simply now by the length of the complementary interval. So if you now want to define, take, I draw this here. So now for x, y in L, we order them as follows. So you have to be a little bit careful because you might have two endpoints in L with the same length of the corresponding complementary interval. So you do something like this. You say this is smaller than x if and only if tau x is larger than tau of y, or second condition, if this is equal, then you order them using the usual order on the reals. So and x is smaller than y in this usual order. And now you can check that this will give you an omega order. Simply because if you take any real number and you look at, you check out what complementary intervals I'll have lengths larger than that given number, there are only finitely many, because essentially this follows immediately because we assume that this Cantor set is compact. Okay. So this gives you an omega order on the Cantor set. And when I said somehow that I gave you this kind of indication, I would say this maybe again today, is that if you have a dense omega order, if you have an omega order set is not so bad. It's only a problem if it becomes dense. And so how could you possibly get a dense omega order set? And this is how it works in many of these proofs. Is of course what you might want to find. Maybe you can in a how could you if you just as an example, if you would have a function maybe continuous such that this one here has interior, suppose, well, this is somewhat dense, it's continuous and somewhere dense, then because the left endpoints, and you can see this here in the picture, the left endpoints will always be dense in the Cantor set. So if you would go down here, you would see that the left endpoints L would be dense in the set of the Cantor set. So then by continuity, you would get that f of L n is dense, somewhere dense. And then hence of L n is can be omega ordered. So in many of these kind of results we say that somehow we say that if you're in a Tame structure, then the kind of the fractal or metric dimension of C cannot be too big. And this is really here where this is coming from, because you always get this omega ordered set. But if this kind of original Cantor set is too large, has too large of a dimension, then you can often find these functions f and the power c such that this is too big, and then you get into trouble. That's really the idea. You have to be a little bit more precise, a little bit more careful. But really the idea here is that you have this dense omega ordered set in this omega ordered set, and you have to be careful when it becomes. Okay, so this is really one of the important examples for me, and I will come back to that a couple of times. Yes.
The two sends the point to an interval, no?
To the length.
To the length.
Right. I mean, yes. I mean, so you can. So I mean, if you want to make this definition precise, you would probably for even every would also define the right endpoints. and then you would map X to the right bound point, and then you would simply take the difference between would be R of X and R of X. That's all definable. Okay, so now I wanted to say a little bit more about this. I want to finish this picture of expansion of the additive group. And for that, one of the kind of, I think it's a very great result for the expansions, for minimal expansion is the Peterson Senko trichotomy. So it really tells you that in general, how the kind of o-minimal structures look like in terms of are they linear, they're trivial, are they nonlinear. And so in this kind of generality of type, about what I call type A structures, or what I'm going to type A structures, we got to get something similar. And so for that, I define here briefly what I mean by a structure of field type. So, okay. So in our setting, so for now, if I talk about an expansion R, I still talk about the expansion of a real additive group. And we say this is field type. We say it's field type if and only if there is a field definable in R. So that means that, sorry, let's make this here. So that the graph of addition in this field and the graph of multiplication is definable. And this one here, and this kind of not just some field definable, is an interval. Okay, so you have this on an interval in R, you have this field definable such that it's order isomorphic, such that this is order isomorphic to, so with the usual order to the real field. So you not only have a field definable, no, this is what you have is that it's lives on an interval, and with the usual order, it's order isomorphic. So that is much stronger than per se than just saying that there is some field definable somewhere, even interpretable. Okay, and so now the result I want to state in this kind of setting is kind of the most general. That's not the most general, but really what we know here is that if let R be field type, then R defines dense omega order if and only if, and this is kind of the defines every compact set. So in particular, I think.
So R here is an expansion of the ordered additive group?
Yes. So if you have an order, you have field type, you have anything like that, you can even further reduce that if you want to really, but I want to just state it like this here, to expansions of the real vector space. So if you we don't even need this kind of multiplication, but we just scalar multiplication for every alpha is defined. And now this kind of allows me to somewhat finish the, some sense, the picture I tried to draw last time. So now for expansion of the real additive group, we have these kind of two questions you can ask. So you can, the one question you can ask is whether it's of field type, and you can ask whether it has a dense omega orbital set. So this is field type here. And this is dense, see this, dense omega order. And so now you can, of course, in both situations, you can have say no, and you can say yes. Okay, and so I think of the dense omega order as something that determines how tameness or wildness of the structure in geometric sense. And then the field type is, of course, this kind of questions like, I mean, originally coming maybe from Zilbert's trichotomy, that you want to know if you some of you would hope that you get something like, okay, if you are not linear, then you're field type. And so that's really what we can show here. But let me first collect this result over here. So if you're dense omega order and field type, then you define every compact set. And so then this is for us, and this is wild. I'm gonna say a little bit about this one here in a moment. But let me first say something about over here. So one of the things that you would want to have is that these structures here, they're not of field type, so you want to have a strong linearity. And indeed, this is something you get, and I'll tell you why. And the result you get here is that continuous functions outside nowhere dense set are locally affine. Okay, that's not a make a statement precise in just a second. So what this means is that, let's say you have a function from the reals to the reals. You throw out an over dense set, and then on the complement, and on each of the connected component of the complement of that set, the function is affine. So really locally, this is an affine function. Okay. So now I want to say a couple more things. So I will say a little bit more here, and I will say a little bit more here, and I fill this both in while we go along. I already want to give these things names. So this one here, this kind of top right quadrant, we call type C structures because of them, everything defines a compact set. This we call type B, maybe for Vichy, because I will say this just in a moment, what happens down here. And then the whole thing here on the right-hand side, so all of this we call type A. And for my intents of purpose, I really think of this type A, and I will say a little bit more about that in a second. This behaves very differently than type C and B, and much better. And so we'll prove some kind of weak analogs of results for o-minimality in this kind of type A setting. So for me, it's always the kind of the minimal, or the kind of the maximal generalization of o-minimality. So if you want the kind of weakest or most generalization of o-minimality in this setting of expansion of the relative group. Okay. I can move this up. Sorry. Okay, so the main thing I want to talk, that I want to state, first of all, explain you a little bit where this kind of thing in the bottom left corner comes to, so this kind of Senko result. But before I do so, I want to really tell you where this again, where this tameness comes from. And I'm going to prove some of this in the setting of the field on Friday. So the first thing I want to talk again is about, we had this notion of these sigma sets. So these sigma sets were this kind of definable analog of F sigma sets. So we defined them back when we defined it in the case of fields. We really did it something like it was supposed to be a union of compact sets. Okay. That made sense over the field, and so the end it was supposed to be increasing. So something like this. In the field, that the increasing or decreasing the difference didn't matter, because you have it can always take the inverse. So if this is a increasing family, you can just reindex that and make it a decreasing family by taking the inverse. In the case of additive groups and expansion of additive groups, you don't have the inverse, you don't have a pole. So we've changed this definition here just a tiny bit. So we add this kind of second parameter, and so in one parameter this is increasing, and then the other one it's decreasing. So this should be smaller or equal, and this should be the other way. But other than that, this stays the same. I'm not going to talk much about this, except for this. I want to make it clear.
And the XRSs are from a definable family.
Yes, sorry, yes. So XRS is a definable. In whatever expansion you're currently working in. And so the kind of the theorem that we have, or that everything makes everything work, is what I mentioned this already, is a strong bare category theorem, which really now says that let R be type A, then every d sigma set is either has interior statement, and let E subset R to the n be d sigma, then E either has interior or is nowhere there. There's nowhere there. I'm going to prove this in a case of real fields, but next time. Today, I think I just want to. Yes, this I just want to do this. I just want to say everything I want to say about additive groups, and then, or expansion of the additive group, and then we move on. And so I'm also going to prove essentially something like this, and it's much easier in the case of fields. So now what this allows you to do is to move over results that you have for o-minimal structures, but in this more general say. For example, you could move the monotonicity theorem over. So, but of course, what does the monotonicity theorem says for o-minimal structures? That you have a function from R to R, you throw out a finite set, and outside this finite set on each connected component, the function is either strictly increasing or strictly decreasing or constant. Now you could do the same thing here using this theorem, but of course what you have to throw away is not a finite set, but an overdense set. But this all works. The one theorem I want to state here is the following, and this is then gives you this kind of linearity almost immediately, is should keep my numbering here. So this was 210 because the picture was supposed to be 209. This is now supposed to be 211. So let R be type A, let K larger than 0, and let F from U to V be d sigma. So here, when I say a function is d sigma, I of course mean that the graph is d sigma, and I want U to be open. R to the n is open. Then there is a nowhere dense set V. It's a nowhere dense definable set V subset of U such that F is CK. F is CK on okay, so this is, I mean, this is okay, 2 points I want to point out. So that says if you have a type A structure in an expansion of the real additive group, and this really I want to stress this here, if you work over the field, that's much easier to show. But here in the case of the expansion of the additive group, I mean, differentiability is not so easily definable, right? So there's the same result for expansion of the o-minimal expansion of the additive group. So then the what you of course have to throw away here. So I mean, if this, let's say, would be a subset of U and this would go to R, then you would throw away a finite set, and here you saw different nowhere dense set. But you really have to work quite a bit here. The proof in the case of o-minimal structures, we use cell decomposition theorem, but we don't have any cell decomposition theorem. Okay. So now, how do you get to this result? So what we know is that since we're in this kind of type A case, we know that now outside the nowhere dense set, we are CK. So now if you want to, what you now want to do is, you suppose you have a function that is not locally affine outside the nowhere dense set. How do you get the field? So how do we get this kind of field structure living on the reals? And again, this is essentially due to Markov, Peterson, and Philipp. So because they showed essentially that for o-minimal structures, but this really works out in the far larger generality without any substantial changes. I mean, for that one, you really had to work, but here it's really just the same, almost the same proof. So if R defines a C2 function, C2 non-affine function, let's say from some interval I to R, then R is field type. So this is really kind of the same argument that goes back to Silber and Rabinov, but this was already, I mean, in this kind of paper. I think what they literally showed this for in an expansion, in an o-minimal expansion, but the proof is really the same thing. So now you get this this statement here, statement in type A structures with no dense ohmic order, simply by applying both these theorems. So you take a function, let's say from R to R, you apply this generic differentiability, and you say make sure that on each of these complementary intervals it's C2, and then you get field type. So this gives you that outside a non-affine set, you really get this kind of linearity. Okay, so let me maybe fill this the last two things. I have enough time to fill these two things in. So at the very least here you have quite a few things. You have the strong back category theorem, you have this generic differentiability, and so on. The one thing that we're still missing, and I think this is kind of this connected to this Miller's conjecture that I mentioned before, is that, I mean, this what we're missing here is the cell decomposition result that we still don't have. We would like to have. Okay, I will say just a little bit about in the last 10 minutes or so. I talk about type B structures. I do want to say again, I mean, this is in a joint paper of me and Eric, but this whole tetrachotomy, I mean, this is really Eric's idea. I mean, the idea of looking at this this dense omega order and this yes or no and tameness. Okay, that might be happening around, but then also this kind of idea of then comparing this to field type and actually getting these kinds of results. That was really Eric's idea. Okay, so now I want to talk a little bit about type B structures. Here we get, I mean, if I say this already now, but I think I want to say a bit more. What you here get, at the very least, you would hope that you would get some kind of linearity here too. And what you do get here, but this is more or less the best we currently have, is that every C2 function is affine. But really, this comes from very different reasons, and I want to talk a little bit about those reasons. So first, let me give you an example of such type B structure. So I have to give you, so what kind of structure should that be? We know, we erase that if you're of field type, then you're type C, so it must be a structure that is not of field type, but still defines a dense omega orbital set. So let me give you the kind of canonical example for that. So this is 12, so it should be 13. Okay, so pick a k larger than 0, and now I want to give this a name. Let's call it TR. Be the expansion of the reals by, and this will be a ternary predicate, VK. And so this predicate will essentially tell you everything about K area representation of real numbers. So this will hold okay, so this will hold for a tuple, say this is in VK, if the following is true. So if y is in k to the z, that's the power of k, I is in 0, 1 to k minus 1. The idea being that I is a digit in the Ki representation of X at the position corresponding to Y. So let me say this. How do I say this? Y is in there. One I is in there. Is the digit in a K area representation of X at position corresponding to Y. Okay. So in this expansion, yes.
You call this T sub R?
T sub K is better, right?
Okay.
Want to make sure that.
Yes, thank you. Okay, and so this is an expansion of the additive group of integers, and it's a rather expressive one, because I mean, if you think a little bit about this, this allows you to say all kinds of things. This allows you to say all kinds of things about numbers and how their binary representation look like. You could, for example, take all the real numbers. Well, you could take 2 to be k to be 2, and then you can talk about binary expansion. You can talk about whether this and let's say the real number has always zeros at even positions or an odd position, whatever you prefer. Okay, so what kind of sets can you define? So I claim that so you see that this is an expansion of the additive group. I will tell you a little bit more that it says field type, it's not a field type, but I also have to give you a dense omega orbital set so that it's actually type D. And the dense omega orbital set is, you get the following. The underlying set is W subset, let's say even 0, 1. Let W be the set of all x in 0, 1 that have a finite area expansion. Okay. So now this claim is, okay. I think I'm going to show here is that this is dense in this set of 0 and 1s. So the question is, how can you define the omega orbital? And essentially, you now do this the same way you did it for the Cantor set. So let's now take M be a function from W to k to the n, okay, to the z, okay, to be safer, such that, map x to the largest x that this map x to the largest y in k to the z, such that the digit of the finite area expansion of x is 1. Today. Okay, now you can think about how you could possibly use that to do an omega order, and then you do it, not surprisingly, in exactly the same way that you did it for the Cantor set. You say then x1 is all x1, where these two live in W, if either mx1 is larger than mx2, or then we do the same thing. If they're equal, then we order them using so if you want to fill up this, if you think what this should be, is really, if you draw this interval 0, 1, then okay, maybe I do this here, doesn't matter, then I don't have to worry about it. And here, then the first thing here is 1/2, because the binary representation if is really, I mean, 0, 1, dot, dot, dot. Then the next one here is, so in this case, I should write this. Let's look at k equals 2. Then the next one, the next two binary is then there was 1/4. That should be 0, 0, 1. And sorry, now I have to do this. Oh, that's correct. Okay. Yes, sorry. Yes. Then here, this was the largest digit, and this was 0. Then here, the next one here is that is 3/4. So this should be 1, 1, 1. And so here, this is the largest digit again. And then you keep on doing. Right? 1, 8. And so this obviously, this gives you an omega order of this. I should say why this is actually a field type. If it wouldn't be a field type, so sorry, why is it not a field type? If it would be a field type, it would be type C and define every compact set. Then in particular, it would be undecidable. The theory of this structure would be undecidable because it would define a graph of multiple, can essentially define an isomorphic copy of second order arithmetic or anything you like. But in this case, what you can show, and you see, is that this one structure here, Vk, is mutually interpretable with the following structure, with something I really, in the sense of Tame geometry, never thought about the following structure. This is a two-sorted structure. These are the universe. And membership here is the usual membership. So if you have some small x and some capital X here, that this holds that x is an x. And +1 is a function, the usual successor function on that. And you can really, if you think about this for a little bit, it's not so hard, in particular in the case that k is equal to 2, but this works on every, that these structures are really more or less the same. Because you can think, if you think of binary representations, you can think of a real number as a sequence of 0 and 1s. Okay. And well, subset of the naturals is also somehow the sequence of 0 and 1s. Then membership here, so then membership really comes whether or not a digit is 1 in the binary representation, +1 is clearly in there. But really the only hard thing is to show, well, it's not that hard, is to show that under this interpretation of thinking as real numbers as subsets of n, you can actually define addition. But addition, I mean, you know, in binary is just this usual kind of carry algorithm, and you can show that this is definable here. And so this structure here, and this is an old result of Clichy from the 62 or so, this is decidable. And so the theory of this one here is also decidable. Indeed, we really don't have any other example of the real field of type B structures, which is not mutually interpretable with some expansion of this thing. So for as far as we know, all the kind of type B expansion that we understand come from this thing here. Yeah, I mean, that's really about this. So what I'm going to do next time is I will move on from the additive setting, and I will talk about go back to the scaling of the field, and actually I'm going to plan to prove this strong back category theorem next time. And I'm going to do this on Friday.